Hello everyone and welcome back to another video here in the Hidden Quantum Champion series. Time measurement, or generally measuring different things in our environment, plays an important role because as we are trying to build AI, as we are trying to increase our communication systems, those measurements, they can play critical roles. So time measurement, for example, is important when it comes to all kind of networks, be it the internet itself, being the communication between ground and satellites, for example, for GPS, but then also high frequency trading applications. So there are many IT applications that need precise time measurement. And that's something where quantum sensors play an important role. But also when we talk about training new models, AI models, then we need data. And data is something that can, for example, be collected using sensors. There are certain new types of sensors, like quantum sensors, that enable us to get new kind of data sources or measure data in a higher precision than ever possible that can be used, for example, for AIs, but can also be used for classical things like using, for example, the magnetic field to identify which position you are in or something like this. We've talked about these in previous episodes. And if you haven't seen those, go check out the Hidden Quantum Champions series. But today we are going to look at a company called QuantX, so Quant and then X, or QuantX Labs, that is working on these types of sensors. And today I want to talk a little bit about how these sensors actually work, like how they are functioning and what QuantX Labs is doing. And with that, let's get started right into today's video. As per usual, make sure to get yourself something to drink because we are talking about a little bit about the physics today. You don't need a physics degree to understand what I'm going to explain. I will try to make it easy to understand because I think these are important concepts that play an important role as the number of quantum technologies in our daily lives probably will increase at some point. And with that, let's jump right into it. So here we are on their website and it says Precision Unleashed, and you have this very cool X here in the background with this effect. So when you move the cursor, it also tilts its position. And then there's here this little command to scroll. Let's do that and let's see what we can learn here. So quantum sensing, precision timing, this is what I've been talking about. And then we see here the applications, right? Defense, space, and critical infrastructure. So what is the company doing, right? What we do? So solving tomorrow's positioning, navigation, and timing challenges today. Conventional positioning, navigation, and timing, PNT infrastructure is fragile. It is to build on weak signals, backup networks that lack resilience, and it fails the moment that adversaries jam it or GNSS goes dark. So that's I think the satellite network, right? QuantX builds quantum sensing and precision timing products engineered to hold accuracy no matter what the conditions, so that modern networks, critical infrastructure, and national communication remain secure today and powered for tomorrow's needs. So here we see that the target of the way that the company is positioning itself is very much towards critical infrastructure, towards national needs. And then, the world is waiting and resilient PND. We are already delivering it from contested airspace to contested orbits, from over the horizon radar to telecom networks. QuantX products are designed to meet the most rigorous of demands and supersede incumbent solution in the environments that require precision and resilience. So we see they're positioning themselves for these national, infrastructure environments. And one of the, main selling propositions here is that this is in fact not lab instrumentation or anything, but stuff that is rugged, that can go into the field, that can go into the airspace, and that can be used in the, relevant environments for this kind of infrastructure. There's also some call to action here to discover the network and see the momentum, but we will not do that for now. We will look at the different products for now. And here we can see them. So there's Cryo, Ultra Low Phase Noise Oscillator, Tempo, Compact Optical Atomic Clock, Sentio, so Compact Ultra High Performance Quantum Magnetometer, and Synchro, Precision Time and Frequency synchronizer. And we will talk about these in a couple of minutes, but first let's move down a little bit further here. So the tech foundations developed by real-world renowned physicists, brought to life by engineering expertise. We see here atomics and photonics, so use quantum energy levels for atoms to create ultra-stable optical clocks, delivering resilient GNSS independent timing signals. And then photonics combines ultra-stable lasers, optical cavities, and frequency combs to turn atomic transition into accessible precision timing and sensing signals. Here we see the different breakthroughs that they are associated with. So the cryo clock founded, cryo clock limited, established to commercial cryo, IP transferred from Adeline University. Then we see the BAE Phase 0, the Eureka Prize. That's all regarding the cryo product, which we will talk about in a couple of moments. Then we see the Avalon Airshow rewards, defense co-development. So since 2020, well, actually here in this airshow probably already since 2019, we see also this focus on the defense-related topics. Then we see here Lot 14 launch, Quantum Technology Challenge, QuantX Labs rebrand. So that's when they changed to their current naming. And then in 2022, we see the Tempo product being added, Space Agency backing, ASCA contracts, Defense Trailblazer. And now in 2026, where I'm recording this video, Tempo is in the orbit. So this is the atomic clock, I think, that we've seen here before, right? Let's scroll back. Tempo, optical atomic clock. Tempo subsystem is the first optical frequency come to reach orbit aboard exotrails space Vanuatu via SpaceX Transporter 16. Here we see the leadership team. So Chief Executive Officer and Director is Andrew Luton. And then, we see here Chief Operating Officer, Chief Financial, Director of Product, and so on. So it's a company with multiple different functions in there. You have the leadership team, you have the governance board, and so on and so forth. I'm recording this in end of May / beginning of June of 2026, and we see here last news from end of May 2026. So the news portion is relatively up to date, very much up to date, and it says QuantX Labs announces broad chair transition, and then ready to talk position, get in touch as per usual. And down here we see established in 2016, QuantX Labs is a privately owned, highly respected Australian company and a world leader in high precision timing and quantum sensing technologies, so Australian-based company. Now we also see here, right, for University of Adelaide, which we also saw before where this kind of spun off from. Now quickly on the products. And here we see different ones that fulfill different purposes. Unfortunately, most of the information is hidden here in these data sheets. So if you actually want to learn about the details of these products, I encourage you to go check out the website, because there you can download those and learn a little bit more. For today's video, you have to trust me to talk a little bit about that and how these actually go together. But I have looked briefly into these data sheets before, so that's how I got the information that I'm talking about now. So cryo is the ultra low phase noise oscillator. It says ultra pure signal oscillator with world beating close to carrier phase noise and short-term frequency stability, built for over the horizon radar, deep space tracking and high precision timing, where conventional oscillators limit systems performance. Export ready, commercial version available, easy installation, fully autonomous operation with low maintenance circuits, and then ultra stable time and frequency signal, no cryogenic storage need for operation, and turnkey full autonomous self-contained, user friendly. Now, quick step back, let's talk about oscillators and timing. So in the old days, and that's probably something that we can all still very much relate to, especially after the pandemic, where mechanical watches became super famous on social media. In the old days, most of the time measurements were done, time measurement was done with these mechanical watches. Before that, there was the sun clocks, right, where you would use the sunlight to kind of measure roughly what time it is. But of course, there's certain reasons why this is not really, let's say, easy to do, because you have to fix the fixture somewhere. You can't really take things around with you, and also it is hard to get access to that for specific applications. And also probably the precision is not super easy to tune with those. Now entering the world of mechanical watches. And in mechanical watches, usually what you have is you have some type of energy source, like a spring that you are using to store mechanical energy. And then you have some kind of oscillator, something that is swinging, that is kind of creating a swinging motion that you then use to trigger the whole mechanics that will then translate into the whole gearing of your watch, and then create those like second ticking. Actually, some of them, they tick 4 times per second, right? And so on and so forth. Now, these oscillators, they're actually not so easy to build in a way that they are like on a long term giving you a good timing. And that's also why this whole watch industry becomes so super sophisticated, because building those devices mechanically in such a way that you can measure pretty precise the time is actually a huge challenge, and it requires a lot of mastery to actually produce something that even in like a moving piece, like a watch that you're wearing on your arm wrist, or generally on your wrist, is still showing you the right time. There are many different complications about that, and I mean that's what triggers also the interest and what makes it such a nice thing to look at on social media. Now, looking at this on a long term, this was probably not the best way to do things, and that's also why at some point the quartz crisis came along. So quartz crisis is when the electronics was developed. The quartz crystal basically has been developed and has been used to measure time. So that's when basically all these, let's say, electronic watches came in, right? And now we could make at a fraction of what a mechanical watch cost, you could create something that is much more precise using electrical signals and quartz crystals. Now, this watch that we are looking here, this cryo system, is more or less a hyper-tuned on steroids version of this very early crystals, because it uses a sapphire crystal and it uses a very interesting effect. Now, this effect is something that you know from your everyday life. So, well, maybe not from your everyday life, but it's something that you can experience in your everyday life. And now we move on to architecture. So let's think about a huge amphitheater or like a huge cathedral. I think it was the first time where in a cathedral it was developed or uncovered this effect. If you are building a huge building with a bow, like where you have a wall that is kind of curved like this, and you are standing on one side and whistling against this arc, against this wall that is in this arc shape, you can actually hear the exact wording on the other side of the arc, because of the way that the signal, in this case the waves that you are producing, the sonic waves, so the sound that you are producing is traveling along this curvature and is getting reflected in a very nice way, so that a lot of the signal is actually making it to the other side. So now if you would have two people standing on the opposite side of this arc and one is talking against the wall, like whispering against the wall, the person on the other side can still hear it. And that is a very interesting physics property of such a curved shape. Now looking at crystals, the crystals, they can actually also interact in a way, but they don't necessarily interact with sound, but you can make them interact with electromagnetic waves, so with light. And one specific one is microwaves. So microwaves are light at a very low frequency. You know them probably from your microwave oven that you use to heat up your food. So what happens there? Well, you're creating an electromagnetic wave that actually gets the molecules within water to oscillate. So your microwave is an electromagnetic source, so a light source that is creating a light which has this very specific property that it can make water molecules, so the H2O molecules, it can make them oscillate because they have a bipolar property. They are not exactly electrically equal because of the way that they are shaped, right, in this H-bridge kind of setup. Now you create a specific frequency and then you can start to get them vibrate and oscillate. And that's basically what is called heat. So that's how you heat up your food. And that's also why it is very easy to heat up things that have a lot of liquid, a lot of water in them in the microwave. And that's why it's not so easy to defrost something in the microwave, because there you have ice crystals and it's not so easy for the molecules to start swinging because they're in this crystal shape. And what you technically do is you turn on the microwave very short, you create some heat, and then the ice starts to melt, you wait for it to melt, and then you turn on the microwave again, and so on and so forth. Now back to cryo, back to this product that we've been looking at. We have a crystal here, a sapphire crystal, and you're using these microwaves to actually get the crystal to start to oscillate, similar to the water molecules in your water. Now you make the crystal vibrate. And if the crystal is in this exactly round shape that I was talking about before with the arc that we were looking at from architecture, then you can actually create a system where the wave keeps running around in this loop. So you're now injecting a microwave frequency from here, and then it starts to run around in this circle, and the circle goes of course in the other side back because it's a cylindrical crystal, and now you keep it up and running in this crystal. Now this can already work quite well if you are sitting at room temperature, but if you then cool down this crystal in a cryogenic environment, like here in this product from QuantX, then you can actually reach factors where it's millions and millions of times running around in this crystal. And what you can do now is you can take a detector on the other side of the crystal. So here you have the injection of your signal, and then it starts to run around and it amplifies itself in the crystal because you keep injecting, and it specifically matches the one frequency that can constructively run within this crystal. So the one frequency that matches very well to the diameter of the crystal keeps amplifying itself, and now you put a detector on the other side that measures this frequency and creates then again a closed loop with the frequency that is being injected. And that way you can create a frequency that is very, very, let's say, stable and at a very sharp specific frequency. And that's what this is about. It is a oscillator that creates a very specific frequency at a very low noise and a low phase noise as well. Now, what is the problem with these types of systems? Well, they work very well when you want to do specific, like short time measurements. Like, let's say you have a frequency of, I don't know, 6 gigahertz here. Then you can measure on a very short time scale very, very exactly with this system, this frequency, because the output of this oscillator has such a low noise, because it's this self-amplified loop that is using this physics property of this whispering effect, right? However, on the long term, this might not be the case, because the crystal can start to deform after some time. There's some degradation because you have this constant vibration, right? It's in this constant mode that the waves are traveling through the crystal. Also, it is sitting in this thermal chamber here in this cryostat, and there might be some minimal temperature variations over time that can cause a shift in this frequency. So if you want to measure long periods of time, it is not actually that easy with such a system, because it is measuring very precisely on short times, but on long times it is less precise. And that's where, surprise, surprise, the second product comes in, the Tempo. Tempo is a compact optical atomic clock. It says optical atomic grade clocks that provide ultra high timing stability for terrestrial and space networks, provides resilient high compact resolutions to ensure that critical infrastructure like ground stations, telecom networks, data centers, and trading systems hold constant time no matter what. Developed in partnership with Adelaide University, this Nobel Prize winning breakthrough in next generation of optical atomic clocks, surpasses incumbent microwave clock technology, low size, weight, and power, so SWAP, deployable PNT solution for land, sea, air, and space, and then ruggedized for LEO and MEO constellations. Now, what are atomic clocks and how do they actually work? Again, you need to look into the datasheet to find some more information. I think, if I remember correctly, this one is a rubidium clock, and that one is actually operating on the 6 gigahertz that I was talking about before. So how does that work? Basically, you create a little vacuum cell, which is completely empty, so you evaporate it, and then you put one specific type of atom in there. In this case, rubidium. You can go into your atomic, into your atomic table, and you can search for the rubidium in there after this video. But rubidium is one specific atom, and that has one very specific property. It has a transition from its ground state into a higher state, but then it decays into another state, which is not the ground state, and there it sits stably. So this is kind of like a specific energy state. So if you now, for example, throw some light on this rubidium cloud, it will actually create a transition where the electrons, so you have the nucleus, which has the protons sitting in it and the neutrons sitting in it. Then you have the electrons that are moving around the rubidium, or that are sitting in these different orbits. So they are basically electron clouds that are distributed statistically around the nucleus. And now these can sit in these different orbits, and these different orbits, they are quantized, so they have specific levels. Now in the ground state, every single electron sits in the lowest possible energy level. So that means, for example, in the s orbit, you can have 2 electrons, one with the spin up and one with the spin down, and the s orbit is the smallest orbit. So if you, for example, look at helium, you have 2 protons sitting in the nucleus, so you have 2 electrons to make it balanced, right? An atom is always balanced, and that means both of your electrons are sitting in the shell of this helium atom, and they are sitting in the s orbits with spin up and spin down. Or if you have an H2 molecule with 2 hydrogen in there, same story. Now, if you're looking at rubidium, there are many more there are many more protons, so you also have more electrons around. I think it's like 68 or something. I'm not completely sure about that part. You can look it up later on your periodic table. But now you have all of these electrons sitting around, and they're all sitting in the lowest state. Now, if you shine light with a specific frequency on that, remember, light is an electromagnetic radiation. So now the electron, which is an electric particle, it can absorb this energy from the light. So the light is called a photon. The electron can absorb this photon, and thereby it gets catapulted into a higher energy state. So now you can excite an electron from this low energy state into a higher energy state. And now what happens with this is, now the electron is moving up there in its excited state, and it will fall back down at some point. And that's a statistic process at which this happens. So that's a quantum mechanical thing. We associate those states with a specific lifetime. It can be very long, it can be very short. It depends a little bit on the properties of your atom. Now, the electron falls back, but it doesn't necessarily have to fall back into the original ground state. It can also fall back into another state. That always depends on the transition and the lifetimes that are associated with those transitions. And in the case of rubidium, it doesn't fall back into a ground state, which we can call G, but into an elevated state. Let's call it E. So the electron goes from G, from the ground state, via the photon absorption into the excited state, and then falls back into the E elevated state, which is not the same as the ground state. It can sit there for a long time. What does that mean? Well, actually, if you're looking at this vapor cell, if you're shining light on it, at the very beginning, all of the light gets absorbed. So because the rubidium atoms, the electrons, they're absorbing this light to get excited into this higher state, but then they fall down into this excited state, into this E state, elevated state. Now the transition to get up again into the excited state is a different one, so they cannot not absorb anymore the light as in the previous case. That means now basically the cell becomes transparent again because the light is not absorbed anymore. Okay, now you might wonder what does that have to do with a clock? Well, now you could have an additional microwave generator that operates at this specific frequency, like the 6 gigahertz that I was talking about before. And that is the exact difference between this excited state or elevated state E that I was talking about, the second state that the electrons are falling into, and the original ground state. And now you could create with this microwave generator a case where, or a signal where the electron falls back into the original ground state. So if you hit exactly the right energy, if you're radiating with the microwaves exactly the right photons into your rubidium gas cell, that means you get the electrons back into the ground state, and that means they can again go up into the excited state by absorbing the original light that we were shining into the cell. And that means you have now a system where you have two specific transitions, namely the transition that goes from the ground state to this excited state via the light absorption, and the second transition which brings your electron from the elevated state back into the ground state. Now the one of them is the light, right, that we were shining on it. So the light we can now measure with a detector, and if we do so, we can see if the vapor cell itself with the rubidium vapor in it is transparent or if it's an absorption state. Absorption means we can excite electrons from ground state to this elevated state, right? Now, if, let's say, we don't hit the exact frequency with the second light source, with the microwave light source, we cannot get the electrons back into the ground state from this second state that they fall into, right? And that means the vapor cell will become transparent. There's no light absorption. So we can measure with a photodetector. We have a light source here. We shine through the cell and we measure with a photodetector. Okay, now the cell is very bright, so it's transparent. That means our microwave generator that is generating these gigahertz signals is not at an exact state where it can actually convert these electrons down back to the ground state. Now we can tune the frequency of this microwave generator, and we can do that and at the same time with the photodetector observe the brightness level of our vapor cell, of the light beam that is going through that vapor cell, and thereby we can figure out at which point we have tuned this microwave generator to actually fit exactly this frequency of the rubidium atom. The cool thing about this is it's basically a piece of quantum technology. It's using single atom energy level transitions of rubidium atoms to be able to fix this specific microwave frequency, these 6 gigahertz that I was talking about, to convert from this elevated level back to the ground state. And that's extremely interesting because now we have figured out a way to use the properties of an atom that are not changing. They are inert to the atom. So you can put it wherever you want. It can be on the ground, it can be in the space, wherever you like. The atom's properties are always the same, so it will always have this transition. And you can use this in order to fix the signal of a frequency generator, like a microwave generator, for example. And now you can take this microwave generator again as an oscillator to measure time. So you now have built a clock that is very, very stable over a long period of time because it doesn't have any drift, because the drift is basically removed by the properties of the rubidium atoms that are fixed over time. They are constants, right? As long as rubidium is rubidium, it will always have exactly this specific transition, this specific energy transition that is connected to this photon power of the microwave photon, and that is connected to the time. So that creates your clock. Now, these atomic clocks, they work very, very well over long periods of time because they don't have any drift. However, on the short time window, they have some points where they're not exactly precise. And that's because of different facts. There's something called shot noise that is related to the detector that you are using, so the photon detector. There is some also general lack of precision because of the way that these setups with the vapor cells work, because usually you don't run them completely continuously, but they're running in loops. And if you are running in this loop configuration, there's always some time where, let's say, your oscillator is not exactly tuned due to that loop. And that's now where the combination of what we've seen here with the tempo and here with the cryo, where that becomes very interesting, because the atomic clock is very good at measuring long times, and the tempo is very good at measuring long times, and the cryogenic oscillator that we talked about before is very good at measuring short times, especially if you put it in this cryogenic environment where the oscillator quality factor, the so-called quality factor, becomes very high. So the waves are traveling very well within this sapphire crystal. And if you shield it very well, so that you make sure that there's no like cross absorption of the microwaves with the inner shells of the cryostat and so on and so forth. But if you are managing to get both of them set up in a very well way, you get a system, a time measurement system that is performing very well on short times because of the oscillator and very well on long times because of the atomic clock. And that's generally very interesting for all these applications that QuantX Labs or QuantX has been talking about. Now let's move on to the next product, so Sentio. It is a compact ultra-high performance quantum magnometer. Our compact ultra-high performance quantum magnometer system allows defense, space and mining customers sense what conventional sensors cannot. Sentio's extreme sensitivity, which is smaller than 1 picotesla per square root hertz, allows detection of small magnetic signatures at significant range, calibration free, drift free, and capable of filtering out unwanted background noise to provide clear and precise detection of underground and undersea targets for defense, space, and exploration applications. So it works well at extreme magnetic field sensing, calibration free, drift free, and deployable on land, air, and space. I have talked about these types of sensors before. So again, this is using optical sensing to read out, I think, NV centers. If you want to learn about the details, please make sure to check out the Hidden Quantum Champions playlist, because I have talked about how that works in a different video with some probably competitor, if you want to call it like that, that was also selling magnetic sensors using this quantum sensing technology. Then finally we come to the synchro. So this is a precision time and frequency synchronizer, so the ability to accurately synchronize distributed clocks with critical to resilient PNT networks. GPS has been widely available for decades, and modern society has developed a deep reliance on the precision timing and position signals it provides. Synchro enables precise time transfer over optical fiber and optical free space links, utilizing both conventional and quantum techniques, benefiting applications such as national timing grids, VLBI observatories, energy grids, transport corridors, and financial trading venues. Next-gen performance and security, building block architecture for secure and flexible GPS, alternate timing, and can be used in conjunction with Tempo, Cryo, and Sentio. And that, I mean, makes sense. This is basically combining all of these components that we've talked about before. Now, real-world impact, capability where it counts. So we step in when GPS is denied, when extended sub-nanosecond holdover decides whether mission-critical networks keep operating, and when sovereign supply is not negotiable. Our Australian-designed and built quantum sensing and precision timing systems solve the need of defense forces, space programs, critical infrastructure operators, telecom networks, financial markets, and scientific institutions that modern economies rely and run on. And I mean, yeah, I guess we've talked about these points before. And then, yeah, where their products go to work. I think these are the topics that we've mentioned also previously, where like this kind of navigation plays an important role. And again, then here is the, let's say, call to action to get in touch with them. Very quickly, as per usual, towards the end of each video, let's quickly look at the about part of the company. So about QuantX, a world leader in high precision timing and quantum sensor technologies. We build products for significant and globally relevant programs supporting sovereign capability and the development of technologies that matter on global stage. And here we see the whole team of the company, established in 2016, headquartered at Lot 14 in Adelaide, South Australia, a global leader in precision timing and quantum sensing technologies, developing next generation optical atomic clock and magnetometer technologies. Our expertise is sought after for applications spanning critical infrastructure, space, defense, telecommunication, and navigation systems. We've seen these ones here already. And then again, here we see the full team as well as the awards that they have been awarded with, and of course the call to action to become member of their team. About the values, vision, and mission. So here we see, I guess, the values: bold, so challenge the status quo, empowered to give it a go, excellence, be visionary, strive for distinction, and then trusted to be genuine and reliable, act with integrity. The vision, a secure future built on precision and integrity, and then the mission, to be a globally leading provider of the precision technologies that enhance communication, navigation, computing, and defense systems. Here we see a couple of partners and the government. So we see here Minister of Defense, Head of Global Access Program, Premier of South Australia. So I think there's a lot of important partnerships in here. We see the news section that we've talked about before, right, with the latest news from May. In April, it says QuantX Labs quantum technology now in orbit as Australia commits $425 billion to resilient defense, and so on and so forth. And then a small team making a big impact. Again, become part of the team, and if you're interested in the products, reach out to them as well. I think with that, we are already at the end of today's video. So QuantX, again, one of these hidden champions from my point of view in the space of quantum technology, using quantum sensing, so atomic clocks and magnetic sensing, to actually build applications that are already relevant today. In their case, a lot in the defense sector and in the sovereignty related topics, so communication as well. But generally, I think one of those topics where, let's say, the new quantum revolution, the revolution that is about single quantum systems and sensors, in this case in sensors and in communication possibly, is already playing a big role. I hope you found this video as interesting as I do, or as I did in the research of learning about all of these cool things. If so, please make sure to give it a thumbs up. If you stayed until for all the video until the end, so until where we are here now, then likely you're gonna want to see the next one. So make sure to subscribe to this channel. I'm looking forward to see you in the next video again. Until then, stay hydrated and see you then. Bye bye.